The Chromebooks won't, no. But they'll let you get at your own version of the problem so you can work it in parallel with me. Yeah. You all have different numbers, same question. Nope. Nope, I take your score directly from your score on the assignment. Yep. All right, so we're starting with question number 1. In the package, that was the most requested. A billiard ball travels 21 centimeters in the positive direction, hits the cushion, rebounds in the negative direction, and finally comes to rest 9 centimeters behind the original position. What's the distance and what is the displacement of the ball? So, in your Y, you should have expressed what, that you understand what distance is. So distance is how far you have traveled. And then displacement is how far you are at the end compared to where you started. Let me just finish the sentence and I'll answer. Including direction. All right, what can I help you with? Correct. Yep. And not every problem, but I try to only pick problems that have randomized variables. That way you can confer with someone, find out how to do it without them just giving you the answers. Yeah. All right, so I'm going to do a little diagram here also, just for my own thought process. Uh, 21 centimeters. And 9 centimeters. The ball goes here, turns around and comes to here. Right? Ball goes down, and they said, oops, they defined this direction as positive. Right? Well, it said it went 21 centimeters down, hit the cushion, and then bounced back and ended up 9 centimeters behind its original position. Oh, okay. So you saw it stopping in here. Yeah. Yeah. No, 9 centimeters behind. So, part A asks us what is the distance covered by the ball. And using our definition of distance of how far you travel, I would find the distance as 21 centimeters plus 21 centimeters plus 9 centimeters gives me a distance of 51 centimeters. Yes. I'm kind of in the middle of doing this, but when I'm done with this problem, I can stop and help you. Or maybe one of your classmates can help you. All right? The how's, you actually, once you have your value, I'm not collecting the work for the house. You go right into the site and see how there's a blank that says value. You put in your value. You say submit. And if you get it correct, you get the points. And if you don't, you don't. So that's how you get credit for the house, by answering it correctly. Nope. Huh? What other website? You right now I have it set that you have unlimited numbers of answers. All right. So I'm trying something new this year. Usually I limit it to like 10 or 15, but I'm trying unlimited right now, and we'll see how that works. Just be aware though, if it's like multiple choice, things like that, you don't get unlimited on those. There are penalties. The second one asks for what's the displacement. I'm going to use my definition of displacement of how far you are from where you started. I think I even have an equation for that on, yes, I do. Under constant velocity here, you can see it's delta D equals D final minus D initial. Remember, the direction matters. That's why you have the vector symbols over everything. So I'm going to write that equation. Excuse me. And so my final position is going to be -9 centimeters minus my initial position, which I'm going to call 0 centimeters. And I get a displacement of -9 centimeters. Let's see if that's correct. Yay! Always like it when I get the green correct. All right, on to number 6. What is the final position of an object that starts 7.9 at 7.9 meters and moves with velocity of -1.1 meters per second for 3.9 seconds? Express your answer in 3 sig figs, including appropriate units, and I've already put in the units for you. All right, so number 6. So for your y on this, we look at the problem. It's about where you end up, right? And it gives you where you start. And it gives you how you're moving and how long you're moving for. So I would say, okay, there might be some common sense things here to show that you understand. The faster you move, the further you go. You travel, let's say. The longer, and by longer, I mean time, lead further. I might even put, I start at a positive location, but move negatively. Has everyone started? Everyone looking at your own numbers. Do you start at a positive location and move in a negative direction? Is that kind of true of everyone? Okay. So I'm thinking, let's see, I'm going to start here, and I'm going to say that 0 is over here, and this is where I start, so that would be D naught or the initial. But I'm moving that direction, right? I'm moving to the left if I call to the right positive. So, do you think I'm going to end up at a more positive location or at a more negative location? End up at a more negative location. So I'm kind of getting in my mind, I'm thinking I'm going to end somewhere over here. So if I get a number that's more negative than my starting position, I'm probably going to be pretty happy. All right? Because it's good to get a sense of what you're expecting in the problem. So now I go to my handy-dandy equation sheet, and I've got this nice equation in my constant velocity that says where I end up, that's D, equals where I started, D naught, plus my velocity multiplied by my time, which is how far I traveled. So that equation that's right there on the top line there, where I end up is where I started and how far I traveled because I was moving during that time. That's how you put the meaning of that into English from math. Mathese to Englishies. So I'm going to use that equation. Now, one thing I'm trying to do here in all these solutions also mimic that rubric that you have of what you'll be graded on when you pass in problems like this, like on a test. All right? So that's why I'm very careful to write down my equations, to substitute with units, and do all of those things that are on that rubric. All right? So, let's see. I want to know where I end up. Leave that. I know where I started. It starts at 7.9 meters. So that's my D naught, 7.9 meters, plus my velocity is negative 1.1 meters. Whoops. So negative 1.1 meters per second. And the length of time that I travel for, 3.9 seconds. Do all that in my calculator. You got 3.61. And that ends up being meters. So let's see if that's correct. I think it is because it's more negative than 7.9. So I'm feeling good about it. 0.61. Yes. Yep. All righty. 7. I just erased the 7. 7 was the next highly selected, and then 11. So we've got two objects here, starting at different places and moving towards each other, and the two objects collide 0.65 seconds sometime after starting. This brings up one of my favorite points to remember, which is what must be true for objects to collide. Not necessarily. You can be chasing someone and catch up to them. What must be true to meet or collide or run into people? Say again? Well, I could have one person going this way and the other person cutting across. Football players. What has to be true to tackle somebody? Not necessarily. You can be standing there, they could run into you. No. It's lot easier than that. Hey Joe, I wanna meet with you after school. Tell me, what do we need to know to be able to make that happen? Same spot at the same time. You gotta tell me, hey, I'll be in the LC at 3 o'clock. To catch somebody, the only two things that have to be true: same place, same time. You can be running opposite directions. One can be standing, the other run into it. You can be on completely different paths. You can be catching up or falling behind. But same place, same time. That's important. So to collide must be same place at same time. That's probably the most important point in the SWAT. You know, then you would want to kind of, I'm going to put in here, repeat number 6, right? And because I'm a visual person, I'm going to do a diagram. I'm going to have person number 1 and person number 2. And let's see, the object 1 starts at 25 meters and is moving negatively. Okay? And velocity 1 that way. Object 2 starts at 13 meters. Oh, I'm taking to the right to be positive. Is that okay? And move directly towards object 1. So that means that direction. Right? Now I'm going to use my exact same equation again, the one I just used last time. So writing it in generic terms. And I know that where they collide, some point in here, I'm going to call that just point D. And that's going to be the same for both of them. So for object number 1, I'm going to have D equals D1 plus V1 delta T1. And for object 2, I'm going to have D equals D2 plus V2 delta T2. Oh, wait a minute. Do they move for the same amount of time? Yeah, I think so, right? Yeah, I think they move for the same amount of time. So I'm going to pull off the subscripts on the T because they're the same. So I don't need the subscripts. I only need subscripts when they're different. So my step now is to set these two equal to each other. So I get D2 plus V2 delta T equals D1 plus V1 delta T. Delta, remember, means change. Okay? That's up on our equation sheet too. Someplace. Oh, it's on like the back page of it. There's a on the last page. There's facts and things to help you. Delta changes final mass. There's SOHCAHTOA up there. There's all those fun things. All right, so D2, where where object 2 starts, that's 13 meters, plus, I don't know V2. I do know my time, though, right? 0.6, yeah, mine's 0.65. So 0.65 seconds. That equals D1, 25 meters. I'm going to have to shift things over here. Plus my V1, which is, for me, negative 5.3 meters per second. Times 0.65 seconds. I kind of wrote too big there, ran out of my horizontal space. In my problem, it says the objects collide 0.65 seconds after starting. I'm glad you asked it. It's a good thing. So now I'm going to solve this and find V2, right? So let's see. And just kind of simplifying, I get 13 meters plus V2 times 0.65 seconds equals 21.555 meters. Remember, I don't want to round in the middle. And then, let's see. I end up with my V2 is 13.2, and it's a velocity, so it's meters per second. Let's see if I got it right. I don't. Yay! Now I can do part B. In part B, they want to know that location where they collide. Now, so they want to know D. Could I solve D in the case for number 1? Yeah, I have enough information. And for number 2, I also have enough information now. The only difference is, like on a test, I wouldn't be sure if 13.2 is correct. So I'm going to pick to do it for object 1. So I'm just going to do D equals, this is part B, by the way, D1 plus 1 delta T. Substitute in all the things I know. 25 plus negative 5.3, 0.65 seconds. This is for part B. So I could have actually done this part right away, right? Oh, I know what the answer is. That's good to check. I already solved for it up there, right? It's 21.6. That was convenient. And there was much enjoyment. All right, I'm going to do number 11. That's probably the last one we'll have a chance to do. Number 11, yep. So number 11 says a 0.15 kilogram baseball has a momentum of 0.50 kilogram meters per second. lands on the ground. And they want to know what's the ball's speed just before landing. So my y would be as simple as momentum is the object's inertia and velocity. Yes. The name of this problem set. Motion and inertia, Unit 1, yeah. I don't know which website you're at. I can't see your computer. You're a student. Look up, right? He's got the room number, right? From my equation sheet, I'm going to grab my equation for momentum there in the middle, which is that momentum is inertia multiplied by velocity. I'm going quick just because I want to make sure I get this done. I have the inertia and I have the momentum. It's looking for, I have to finish problems 1, 9, 12. So, all right, let's see if 333 is our answer here. Now, it only wants 2 sig figs, so I'm just going to put 3.3 to make it happen. Yay!